So this article is by National Geographic, and the title is Here's What'll Happen When Plate Tectonics Grinds to a Halt. A new study says we may only have another 1.45 billion years to enjoy the dynamic action of Earth's geologic engine, written by Robin George Andrews and published August 29th of 2018. There's no geological artist quite like Earth's plate tectonics. Thanks to this ongoing operation, we have mountains, oceans, terrifying earthquakes, incandescent volcanic eruptions, and new land being formed every single second. But nothing lasts forever. Eventually, the mantle will cool to such an extent that this planet-wide conveyor belt will grind to a halt. At that point, you can say farewell to the carbon cycle, as well as the constant reshaping and reshuffling of land masses that have been big drivers of evolution over eons. Hui-Ming Cheng, a mathematical geoscientist and president of the International Union of Geological Sciences, is the latest to take on the prophetic role of predicting when this bleak day may arrive. He calculates that the shutdown will arrive in about 1.45 billion years. That's well before the sun is expected to swell into a red giant and consume us in its death, throws roughly 5.4 billion years from now. Here's why tardigrades may be the only life forms that'll survive until the world's end. The study published this month in Gondwana Research has provoked controversy, and some experts argue that we can never accurately predict the end of plate tectonics. But scientists largely agree that such an end will arrive one day, putting Earth on a path to geologic standstill. So what will our home world be like when those major planetary processes give up the ghost? Tectonic jigsaw. Figuring that out means first understanding how plate tectonics work. Earth was born 4.5 billion years ago in the Pyreas of the early solar system. Once entirely molten, the heat generated by its formation and radioactive materials in the rock began to escape. As the planet cooled, Earth settled into its current layered structure, with a dense inner iron core, a liquid outer core, and a brittle upper mantle and crust sandwiching the hot plastic-like rock of the lower mantle. Anywhere between 600 million and 3.5 billion years ago, slabs made of crust and upper mantle, collectively known as the lithosphere, became cold and dense enough to be able to sink into the lower mantle, kicking off the era of plate tectonics. The lithosphere became divided into a jigsaw puzzle of plates that are constantly jostling across the planet's surface, driving geological action above and below the oceans. At the mid-ocean ridges, mantle material rises, decompresses, and triggers profuse melting, creating oceanic lithosphere. The colder and denser edges of the slabs help pull this lithosphere plate away from these ridges and down into the depths. They usually dive beneath a less dense oceanic or continental plate in a process known as subduction. This activity generates explosive volcanoes and a fresh crust at the surface. When two continental slabs collide, they buckle, and mountain ranges like the Alps or Himalaya form. Upwelling mantle plumes can sometimes appear beneath continental or oceanic slabs, and this ever-moving center of melting creates chains of volcanoes. At some point, though, the mantle will cool to such an extent that the slabs can no longer sink into it, and several studies have attempted to predict when this will transpire. Cheng's new paper uses mathematical models to estimate how fast the mantle is cooling, based on what we know about the intensity of the planet's magmatic activity from 3 billion years ago to now. That, he says, gives us a first-order estimate of when plate tectonics will end. On the path to stillness. Regardless of the precision of this figure, plate tectonics will inevitably perish, says Ken Hunt, a research geophysicist working with the United States Geological Survey. When that day arrives, it may well be the end of the world as we know it. Earth would likely enter a single lid regime, a complete jigsaw of titanic slabs that will no longer drift or sink. Mountain building will stop, but Earth will still have an atmosphere, so erosion by wind and waves will shave down the mighty peaks to hilly plateaus. Eventually, much of the flattened continents will be underwater. Subduction zones will no longer exist, so while earthquakes will still happen every now and then, Truly earth-shattering events above magnitude 7 or so will be consigned to history. At the same time, much of the world's explosive volcanism will be extinguished, although volcanoes would not be entirely snuffed out. Mars, a world of failed plate tectonics, did manage to form some impressive volcanic features, including Olympus Mons, the largest volcano in the solar system. Without moving plates, a long-lived upwelling mantle plume focused plenty of crustal melting on that one single spot. While the mantle of future Earth remains warm enough to convect, and partially melt, we would get similar but scattered stationary hotspots of plume-driven volcanism. We would never get anything as large as Olympus Mons on Earth, as our gravitational field is too strong, and anything that massive and tall would simply sink into the crust. Instead, our voluminous volcanoes would be flatter and far more spread out. And, as happens today, part of the lower lithosphere would continue to peel off and fall into partially hot parts of the mantle, particularly hot parts of the mantle. This would cause mantle material to rise in its place, pushing the crust up and forming isolated mountain ranges and associated basins. This activity would cause minor earthquakes and maybe even additional pockets of volcanism. These are processes that shaped Venus's surface, says Robert Stern, a plate tectonics expert at the University of Texas at Dallas, referring to another world without fully functioning plate tectonics. But eventually, as cooling continues, those mechanisms will also cease to be, and the planet's final volcanic lights will be snuffed out. The mantle will be relatively frigid, and Earth will become a dead planet, like Mercury, he says. Perhaps, just before it does, Earth's liquid core will cool enough to end convection, causing the planet's protective magnetic field to fail. The sun's stream of energetic particles will strip away our atmosphere, and its expansion will boil away the oceans. There's not a lot to look forward to after plate tectonics' demise, Hunt says. The planet will just keep getting flatter and more boring, he predicts, until Earth splashes into what's left of the sun. Prophets of plate tectonics. Other researchers have come up with different plate tectonic death dates. One 2016 study used extremely detailed but simplified computer simulations to put the end date at 5 billion years, roughly around the time of the sun's demise. Another 2008 paper used evidence of plate tectonic activity to suggest that plate tectonics are intermittent. Its authors predict the next major pause will take place 350 million years from now, when the Pacific Ocean closes and many subduction zones deactivate. The question is a good one, and yes, it will end eventually, says Stern. However, he fundamentally disagrees with the new study's reasoning. I don't believe any estimated time of death for plate tectonics, he says. Christopher Scatese, an emeritus plate tectonics specialist at the University of Texas at Arlington, suggests that the paper shouldn't have focused on mantle cooling. Instead, it should have based its efforts on the slab pull mechanism, because slab pull rules. Instead of a gradual slowdown, Scatese predicts that plate tectonics will be invigorated during the next 1 or 2 billion years before the conveyor belt ends. He reasons that as the mantle heat flow diminishes, the slab will become extremely cool and dense, allowing them to subduct faster. Hudnut notes that predicting any future geophysical events is, even in the short term, challenging beyond current human capabilities. Despite this, he emphasizes that it's good to think ahead, and while none of the predictive papers are perfect, they do highlight the complexity of the subject matter and where there are intriguing gaps in our knowledge of how our home planet operates. The wildly differing models help clarify our ideas about why plate tectonics happens in the first place, Scatese says. There may be things we figure out about the future that can be applied to the past.